Sound check. Sound check, check. Sound check. Sound check, check. Not bad. Alright. Alright. Oh, yeah. Whoop, whoop. 10:26. And it is noon. Let's get going. So, starting out hot with this problem. Shout out to Sarah for sending this my way. So, what we're going to do here, we're going to work this out by using U substitution, and then might use Excel to evaluate it. Maybe. Actually, no, for this one, this is all by hand. I'm tripping. All right, let's jump right into it. Let me just double check, triple check the sound's working. Evaluate it. Maybe. Actually, no, for this one. Yeah, we're good. All right, let's get into it. So, shout out to Sarah for sending me this problem. In this problem, we are given P prime as a function, and P represents thousands of people. T is the number of years since 1990. And we want to know what was the change in the population, or the change in P, from 93 to 94. And so we want to set up an integral from one year to another year. What years are we concerned with? Well, we're concerned with the years 93 to 94, and 93 is 3 years since 1990, and 94 is 4 years since 1990. So we want to integrate from 3 to 4 the function 18t times the square root of t squared plus 1. So putting this in the format of an integral allows us to, at least get an idea of what we're solving for. So we want to find the antiderivative of this function and then evaluate it from 3 to 4. And so the first thing we want to do is, since it's a U substitution problem, is we want to identify what our U is. So in this case, our U value is typically what's on the inside of some other outside force, I guess. So like in this case, the square root is containing that t squared plus 1. Also, we want to sort of consider, if we took the derivative of t squared plus 1, would that give us a derivative that we could kind of identify in another part of the integral? So like if t squared plus 1 is our u and du is 2t dt, can we see that sort of like a 2t and a dt amongst the other pieces of the integral? And in this case we can, in some sense, right? And so I often recommend, once we find our du as 2t dt, we can solve for dt by dividing by 2t on both sides, and this allows us to perform a direct substitution with a lot of the terms here. So we can leave the 18t, but now we want to, in place of t squared plus 1, put our u, and in place of dt, we cannot forget to substitute in du over 2t, coming directly from here. And so now our goal is to cancel out all the t terms that might still remain. So we see a t on top, a t on the bottom, essentially, so those go away. We see an 18 over a 2, so now we gather the numbers. 18 divided by 2 is just 9. And so What are we left with? We're just really left with 9 times the square root of u du, and we are taking the antiderivative of that. So it might help before we take this antiderivative, I guess we could pull the 9 to the outside since it's a constant. We could rewrite the square root of u as u to the 1 over 2 du. So rewriting it like this allows us to take the antiderivative like a regular power function. So we add 1 to the exponent. 1/2 plus 1 is 3 over 2. The trick is take the top number and add the bottom number on. So 1 plus 2 gives us 3, and then we keep it over 2. Whatever our new exponent is, we always divide by that new exponent. So u to the 3/2 divided by 3/2. Dividing by 3/2 is the same as multiplying by the reciprocal, 2/3. Now if we multiply these, 2 times 9 is 18 divided by this 3. 18 divided by 3 is 6. And so our antiderivative really is this here. And I guess actually we do not need plus c, but before we evaluate the 3 to 4, we need to make sure that we sub back in what u was holding the place of in terms of t. So we sub back in the t squared plus 1 in place of the u, and keep in mind the u was still raised to 3 over 2. So this is what we are evaluating from t equals 3 to t equals 4. So now we can jump right into it. Evaluating an integral means we start with the upper bound, plug it in, and then plug in the lower bound, and then subtract the 2. So we have 6 times 4 squared plus 1 to the 3 over 2. We'll go ahead and subtract the 3 evaluation, write all this out, and we'll go ahead and open up Desmos. Let's get rid of a lot of stuff here. And we'll do the split screen. Make sure we're getting all this. All right. So we'll do 6 times 16 plus 1, or 4 squared plus 1, raised to the 3 over 2. So far so good. That is the 4 evaluation. And then we subtract 6 times 3 squared plus 1, so 9 plus 1, and we raise this to the 3 over 2. And we get 230 as a result. So 230.82. Now let's check out the answers here. It's very important that we recognize this says 230, and the correct answer is this. Now let's justify it. P is in thousands of people. P is in thousands of people. So 230 represents 230,000 people. So as a real value, this is 230,820. And that's where this comes from. All right, let's keep it going. From here, this was a problem that I wish I could remember her name. Let's see if we can find it to give her a shout out. It was Carmen. Yeah, Carmen suggested problem 235F. So I have a couple of them. These will, in fact, use Excel. So let's give that a go. I'm going to see if I can share this while I open up an Excel sheet. Let's get it cracking. This is a great problem, especially the midpoint sum. So let's make sure we can all see this. All right. So the idea here, the goal is we want to essentially find the area under the curve of this function from 1 to 13 by summing up 144 areas of rectangles. Or in other words, we want to sum up the area of 144 rectangles using midpoint sums. Now, what does midpoint sums mean? First thing we need to find out is if we have 144 rectangles between 1 and 13, how do we find out what the width is? That's our first goal, really. So we want to find the difference of 13 and 1, so 12, and we divide that 12 by 144. So I'll just do 12 divided by 144. So the width of all of these rectangles, really, I guess that's just 1/12, right? 12 divided by 144 is 1/12. So 1 divided by 12. Yeah, okay, same thing. So 1/12 is the width. So we also need to consider that if we're starting at 1 and then we're doing 1 plus 1/12, this is the, I guess, like, it's hard to explain. So from here to here would be the width of the first rectangle, but we want to get the height of the first rectangle, not from the left or the right end point of this first rectangle, because that would be doing a left or a right sum. We want to find the middle of these two values. Okay, so how do we find the middle of these two values? So 1.0, I'll just do 1/12. 1 and 1/12. Oh gosh, let's do, how about this? Let's just do this minus this. And then we're going to divide that by 2. And so what this is saying is the first value we should be using should be coming from, let's do this, 1 plus the half of 1/12. Oh gosh, this is getting rough. All right, so the middle, finding the middle of these two values is this value here. This is 1 plus technically 1/24. All right, so starting at this value is where we want to start. This is where we will get the first y value from the function to represent the first height of the first rectangle. Okay, so it's halfway between these two that we are getting the x value that we need to start with. I really hope that makes sense. Sorry, this is super rough, but let's keep it going. I'm not going to waste any time. So we want to start at this x value, and now we can add on the width that we know the rectangles will have each time. So now we can tack on the 1/12, and we get this. So these are the x values that we will plug into the function to get the heights of all of these 144 rectangles. Now, if we click and highlight these and then drag this down, this should fill in. We're going to go to 145 because my smart self started at 2 and not 1. And so from, oh, that's not what we wanted. Holy cannoli. All right, please bear with me. Let's get this right. We're going to put this right here. All right. All right, let's start from scratch. Okay. So we want the halfway point between these two. What we're going to do is equals 1 plus 1.0833333333, and then we're going to divide this value by 2. This gives us the starting x value we want to use. Each time we are going to add on the 1/12. So I'm going to do 1.041666 repeating, because that's what this first value is, plus 1/12. Now, if we highlight these and drag, it should be adding 1/12 each time, and it is not, and that is very frustrating. What am I missing? Okay. So we're going to do it like this. We're going to actually just, all right. Let's figure out what that value is first. Sorry, this is a train wreck right now. All right, this value. I just want to type this value in, 1.125. All right. Now that we have these values typed in, watch what happens, hopefully, if we drag these down. That thing is still messed up. That is so obnoxious. All right. 1.0416 repeating. So now we'll do 1.125. All right. We finally got it. This is going to work, I promise. So this is our x value that we're starting with. Each width of these is now 1/12. So now when we highlight these and drag these down, we're going to be adding 1/12 each time. So we can go to 144, and this will give us the x values we need for our 144 rectangles. If anyone's watching this, I apologize. We're going to bounce back from here. It's only up from here. So Now we want to input the function for this. So we are going to type in this sine function. So in order to type in sine squared of something, I often recommend typing in sine of the inside argument and then taking that whole thing and squaring it. 1.86 times x squared. Wherever we see x, we're going to click on this x value over here and then square that and then close it off and then close off the sine parentheses and then raise it to the second. This gives us the y value corresponding to this x value. And now when we click and drag this down, this is going to fill in all the y values, all the heights of the different rectangles we want to sum up. Now it's hopefully very easy from here. That x value stuff and just really just the finicky stuff of Excel is a nightmare. So hopefully, all right, let's not even talk about it. All right, so the width of each rectangle is 1 divided by 12. And so to sum up all of these rectangles areas, the area of a rectangle is width times height. And so if all the widths are the same, then we can really just take 1/12 times the sum of all these heights. And so we're going to use the sum argument and we're going to highlight all of these. And when we scroll back up, you'll get a better glimpse of what we just did. So the width times the sum of the heights. And then we get this 5.78398. Now what was giving me so much trouble at the start was I kept inputting like a function like 1 plus yada yada yada, and that's just not how we need to do it. So just to recap, summarize what was messing me up. We don't want to start right at the left endpoint because we aren't using a left or right sum. And so we wanted to start with 1 plus half of the width of each rectangle. If the width of each rectangle was 1/12, not the 12th of January, 1/12, they're just messing with me now. All right, equals 1/12. If this is the width of each rectangle, we wanted to take half of that. So dividing this by 2 again gives us this. 1 plus this was the starting value we needed to start at. Then from there, we could add on that width of 1/12. From here to here is 1/12, here to here is 1/12, and so on. And so once you figure that out without, going through a nightmare like we just did, then that's pretty much it. All right, let's start fresh, please, and open up. I'm like scared to look at commas. Y'all are just checked out probably. All right, let's get out of this. We're going to try one that makes a little more sense. So in this problem, we are using a trapezoidal sum from 2 to 18. We want to sum up 164 trapezoid areas. So trapezoidal sum, the formula is essentially 1/2. In general, it's like we'll do it like this. So it's like 1/2 times the width of each trapezoid times the first height plus 2 times the second height plus 2 times the third height and so on, 2 times the third height and so on. And then at the very end, you'll have 2 times like the second to last height and then plus 1 times the last height. And so this is essentially the formula for the trapezoidal sum. Let's talk about how we can actually apply this to this problem. So we are starting at 2 going to 18, and we want to know what's the width between each of these trapezoids, or what's the width of each of these trapezoids if there are 164. So we do a similar thing where we do 18 minus 2, 16 divided by 164. 16 divided by 164 is this. So that probably reduces, but I'll just leave it at that for now. So we'll just use this decimal. This is the width of each trapezoid. So the nice thing is for this problem, we can start at our endpoint. So you only start at your endpoint when you're using left, right, and trapezoidal sums. Midpoints are the tricky ones. So now we want to do 2 plus this width to get to the next one. But I've learned my lesson not to type in the actual function, like the 2 plus whatever. We're going to type in the value, just the number itself. So 2 plus that 0.09 is just 2.097561. And now if we click and highlight these, we should be able to drag it all the way down to 18 pretty evenly. Wherever the closest to 18 is, it would likely be this one. And so it's going to be just slightly off because I've just used the decimal, but that's okay. And there are still, I guess a better question is, did we fill out 164? So maybe not. So maybe I should have backed it up to this, because we only want well, actually we want 164 trapezoids, but that is created with 165 cells or data values, because from here to here is one width, and then from here to here is another, and then so on. So we do need 165 values. All right, so now we want the function values at each of these. So we are typing in this cosine function. Again, it helps to do cosine of the inside argument and then close all that off and then square it. So 1.31 times x squared. Everywhere you see x, you're clicking on the cell A1 or whatever's to the left of what you've typed in. So we have cosine of this. We're going to close this off, so the entire cosine is closed off here. And then we square it. This gives us the y value at x equals 2. Now, this will give us all the other y values. Keep in mind the y values are representing the heights of all these trapezoids. So now we have everything we need. Now what we'll do is input the trapezoidal sum. That was 1/2 times the width of each trapezoid. So that was the 0.097561. And we are multiplying this by, now let's see if we can do this in a clever way. We need just the first height plus 2 times the sum of almost all the other heights except for the very last one. So all the heights except for the last one, right? And then we close that off, and then we tack on the very last height, B165. So everything we have here, we have the width of each trapezoid, the 1/2, we have the width of each trapezoid, we have the first height plus 2 times the sum of all the other heights, because you basically have 2 times each of those heights, plus the very last height. And we get this 7.98, and man, it was so close, huh? All right, 7.67. We're just not having a good day. I apologize, whoever's checking this out here. All right. My guess, I mean, really, it's really just coming from this rounded value here, which is a bummer. But it's definitely making a difference, right? All right. Let's see if we can troubleshoot it real quick, but otherwise I'm not going to waste everybody's time here. Let's see if we can get more decimals here on this value. So we're going to do, wonder how many it'll fill out. All right, we're going to do 2.097560976. And now if we click and highlight these and drag these, let's see if it gives us a better 18 at the end here. Look at that. Okay, so that's a nice 18. So now, did it change our value at all in here? Look at that. Okay, that's kind of relieving, isn't it? 7.67801. All right, so it's all a matter of, did you use, I guess, enough decimals in your width value. All right. Whoever's watching this, thanks for bearing with me. Let's get back to working stuff out by hand. All right. Do something like that. All right, let's keep it going. I don't want this. I want this chat. Then we'll pull this up. All right. Let's get back to basics. So If you have any problems you'd like worked out, if I can handle it, please send them my way. We're going to just go through a bunch of problems I have pulled up for you all that I think are good and just like fundamental problems to review before the final. All right, so the rate of change of A is proportional to the square of W. The rate of change of A is proportional to the product of S and B. So in this case, proportional, if they ever say Y is proportional to X, we are looking for something of this form, Y equals K times X. If they ever say Y is inversely proportional to X, that would be this. And so this is like directly proportional. I'm just going to say direct. And then this is the inversely proportional. And so in this case, because both are proportional to the square of W, W squared, and then the product of S and B, everything is just directly multiplied by K. And really that's it. I thought I had pulled up a different example for that, but big takeaway is directly proportional is K times X, inversely proportional is K over X. All right, let's jump into a Fick's law related one. So Fick's law basically says that the rate of change, I'll just call it, what is it, dc over dt equals, we have K. So Fick's law is like the differential equation. It's the name of the differential equation that we want to use in this problem. So it's basically, I'll just call it like dy over dt. I can't remember exactly what the outside is. And then it's area over thickness times delta C. Delta C is the change in concentration. And so this is what we're using with this. And what they're asking us to do here is to order the following cells by increasing diffusion rates. So we want the smallest dy over dt value first, and then it goes up from there. So we're ordering these from smallest to largest values based on these. And so what we can do is plug these, basically for just each cell, calculate dy over dt. And so for time's sake, I killed a lot of time trying to do that Excel stuff. So we're going to kind of just talk through how to do this. So I'll do it with one, and then I'll leave the rest for practice. So for the first one, cell 1, what we would do is plug in, 5.14 for K. The area, we would literally just plug in 1.85, and then the thickness is the membrane, like this, m times 10 to the negative 9, so 6.35, and then the delta C is the 1.32. You might be asking about this negative 9 business. Technically, what we should plug in here is times 10 to the negative 9 for both of them. But what happens is both of them just basically cancel out, so there's no need to plug those in. So we basically just calculate this value, and then we would do the same with all the other cells, and then order them from least to greatest. So hopefully pretty self-explanatory, but Fick's law pops in, the content a couple times throughout the semester, so I just wanted to include something along these lines for that. All right, let's keep it going. In, I think, the second quiz, there was a lot of stuff about predator-prey models, so I wanted to touch on some basics with that. So in this problem, they say the bears occasionally prey on the otters, but prefer to eat salmon. So basically, the bears are at the top. They're eating both otters and salmon. And then they say the otters' main source of protein is salmon. So the bears are eating otters and salmon. The otters are eating salmon. And then the bear has no predators. So the otters are getting eaten by bears. And in this case, we want to find the rate of change, O prime, so the rate of change of otters in this case. So what we should see is bears having a negative impact on the otter population. So how we would identify that is by identifying where the bears are and just confirming that there is a negative on that term. So it's basically saying the more bears there are, the more negative impact it's going to have on the overall otter population. And then what else do we know? We know that otters feed on salmon, which means the more salmon, the more S there are, it should have a positive impact. So basically, the bears that are eating otters should have a negative impact. The salmon that are being eaten by otters should have a positive impact. And then naturally, the more otters there are, they're going to be competing against one another. So it's sort of going to have a negative impact on its own population simultaneously. I'll just leave it at that. Let's keep it going. Another important piece is the SIR model. So what I'm going to do is reference the Google Doc that I've been working on. Almost done with it. Not really. I'm in the process of working on it. I'll just leave it at that. And what we have here is an SIR model. So this might be helpful to know because there are a lot of problems regarding SIR model. And so let's see if I can pull this up while pulling up this. So in this problem, they ask us to calculate the rate of change of the infected population at day 74. Okay, so what do we know? The rate of change of the infected is represented with I prime. And so if we know that I prime is A times I times S minus B times I, we want to see if we can find all the information in the problem statement that can help us fill out A, I, S, B, and I again. So they tell us that the A value is this 1.58 times 10 to the negative 5. So we can just type that in like this if we want. So I'll just write it out like this. So I prime is equal to 1.58 times 10 to the negative 5. Now we want to find I. I is the number of infected. Okay, so after infection, at day 74, there are 1,947 people infected. Okay, and then we want to find what S is. Do they say how many people are still susceptible? It looks like they say 142 people are still susceptible. All right, and then what else do we know? That many people were covered. I think that's it pretty much. And now we need B. What is B? B is always the number of days. I think I have it right here. You can kind of see it. 1 over the days to recover. And if it takes 24 days to recover, then B is 1 over 24. And again, we need our I value here. That is 1947. So now hopefully when we calculate this, we should have I prime. So let's open up Desmos. Try to make this a bigger screen here. All right. There we go. All right. So opening up Desmos. We want to type in this I prime function. So 1.58 times 10 to the negative 5. All of this times 1947 times 142 minus 1/24 times 1947. And we get negative 1.75. All right, I typed something in clearly wrong. 1.58, 142. All right. Yeah, I missed the 19 and the 47. And as a result, we get negative 76.76. So negative 76.7 is about negative 77 people per day. All right, let's keep it rolling. In the next section, they talked about slope fields. Slope fields are basically visuals of the paths that different solutions to differential equations could take. So in other words, it's basically just if you have y prime as some equation, if you plug in a certain t and y value, it should output what the y prime value is, in other words, the slope, is at a certain t and y location. And so in this problem, they give us the chart of t values, y values, and their corresponding y prime values. So they're telling us what the slopes are at each of these t and y values. For example, when t equals 2 and y equals -1, the slope should be -3 of the little tick mark. And so the nice thing about these is that they lay them out in this 3x3 array, and they should correspond to these 3x3 array of slopes, right? So starting with something simple, if we see that a 0 slope is here and a 0 slope is here, we are looking for 0 slopes here and here. So flat lines there and there. So just based on that, A looks good, B looks good, obviously the answer, and C looks good. So then we want to try something a little more useful. What do we know? We know that here in the top left should be a slope of 1, so a positive slope. And that right there allows us to eliminate C's because that's a negative slope, likely a -1. So then between A and B, let's see what else we know. We know in the top right we should have a -1, so a negative slope. Well, this slope is 0, it's very flat, so we can eliminate that, and then we can see that B does have that negative slope and obviously has all the others. A slope of -1, slope of -2, a little steeper, and then a very steep -3 slope. So all these slopes corresponding to all these slopes, and so on. All right, let's keep it going. What else do we have here? So another slope field, and they're asking which one corresponds to this slope field. So which equation corresponds? And the first thing really to recognize, one of the main things, is these flat line sections. At particular y values, the y prime values are 0. The y values where these occur are y equals 3 and y equals 0, which means if we plug in y equals 0 or y equals 3 in here, the output of the correct y prime should be 0. And so what can we narrow it down to? Which ones of these makes y prime 0 at 3 and at 0? So for the first one, if we plug in 3 here, we get 3 minus 3, which is 0. That checks out. And then plugging in y equals 0 would make this part 0, which means both 3 and 0 make y prime 0 for this one. So A looks pretty good. We can actually eliminate B and D because they have y plus 3. If we plug in positive 3 into y plus 3, we get 6. And so it does not give us 0, which means we would not get 0 plugging in positive 3. So then, for the same reason, C is another possible option because 3 minus 3 is 0, and then plugging in 0 where the y is gives us 0 overall for y prime. So then how do we distinguish which one of these is correct? Really, we could pick any y value we want that we can tell something about it, like that we can tell what's going on the graph. So when we look at this graph, let's say we analyzed y equals 1. At y equals 1, we have all these slopes that are positive. They're going up and to the right. So as we go from left to right, those values are increasing. They're little positive slopes, which means if we plug in y equals 1, either here or here, it should tell us that y prime is positive. When y prime is positive, that corresponds to positive slopes on the slope field. When we plug in y equals 1 to the first equation, we get 1 minus 3 times 1, which is -2. That's why we can eliminate A and choose C, because it's negating the -2 we're getting when we plug in 1. So we get +2, and that corresponds to all the +2 slopes we see when y equals 1. All right, let's keep it going. So In this problem, they tell us that we have an initial condition at 0 and 2.5. They're telling us that t equals 0 and y equals 2.5. So what we can do on this slope field is put a dot at 0, 2.5. And then a slope field, the whole idea is as long as we know where we're starting, we can start at that point and follow the slope field lines to get an idea of what the actual solution to the function y equals would be. So starting at this point, we sort of just like follow these slope lines up, and we realize that the y values are just shooting up to infinity, basically. And so they ask us, which of the following is true regarding y of 4? So they're asking us, what's the y value of this curve that we just sketched? This curve, what's the y value when t equals 4? Well, by the time t is 4, I mean, this function would have already just shot up, just crazy to infinity. But all we need to know is that that y value is greater than 2, because they're defining 2 because, or they mention 2 because it's the equilibrium solution. It's that flat line there. So they are just confirming that it goes up and above that line. And all these other options are describing things below 2 or above 1 or below 1 or above 0. Like they're just all, below where that function's going. All right, this is a great problem. I could totally see this on the final because it combines a lot of things. It sort of combines slope fields, equilibrium solutions, as well as stable and unstable equilibrium solutions. So let's see what we can do. With this problem, they tell us that y equals 8, y equals 1, and y equals -9 are all equilibrium solutions, which means visually we are looking for those flat line sections, those horizontal like slope field pieces, I guess. And then they give us all this information about y prime at different y values. So they're saying when y equals 15, which of course is way up here, the slope values are 8. The y prime values are 8. So really all that's telling us is that we have positive slopes up here. That's it. That's all we gain from that. And then when y equals 4, which is in between here, we know that the slope values are -5. So the slope values are negative in this section. So it's really just giving us a slope. It's giving us the either positive or negative slope in between each of the equilibrium solutions as we go through. So all right, so now for y equals -15, of course that's way down here. I'll just put it there though. We know that y prime is a +7, so positive slopes all through here. And then when y equals -4, which is in between here, we know y prime is negative. All right, so what do we know? We know just by looking at 8 that these lines are going away from 8. These lines are going away from the equilibrium solution as we travel from left to right, which means 8 is unstable. Let's go ahead and analyze the others. At y equals 1, these lines are approaching the line, which sounds like a stable line, but then these lines below it are actually going away from it, which means 1 is not stable either. It's unstable, because for stable you need both lines to be approaching that equilibrium solution from above and from below. So we have 8 is unstable, 1 is unstable, -9 has both lines above and below approaching it from left to right. So this is a very stable solution. And so -9 is stable, 8 is unstable, 8 is not stable, both, yada, yada, yada. We know A is correct. All right, I hope this makes sense. Let's keep it rolling. What's some good stuff? All right, yeah, so in the next section, they were talking about Euler's method. You might pronounce it Euler's. Honestly, Euler's makes more sense, but apparently all these mathematicians call it Euler's, so we're going to say Euler's. All right, so they say to find the solution, given this initial value, you use Euler's method with a step size of 0.2. What is your approximation for 2.4? So what we have to do is basically start at the x value, or I guess the t value of 2. And we're going up by a step size of 0.2. So from 2, we go to 2.2. And then from 2.2, we go up another 0.2, which takes us to 2.4. So the idea is, if we know the y value is 3 at 2, we want to use Euler's method to approximate the y value at 2.2, and then use those t and y values to approximate the final y value when t equals 2.4. That's what they're asking us to find, y at 2.4. So let's talk through it. To find y at 2.2, to approximate it, we want to start with the y value right at 2. Then we want to add the y prime value at the ordered pair 2, 3. So we're using this and this value to approximate the y value of the next one, of the next t value, right? So we want to find y prime at 2, 3, and then we will multiply that by the step size. So let's actually plug all these values in. To approximate y at 2.2, we have y at 2, which is the y value when t equals 2, and that is 3, plus, now we want y prime is up here, when we plug in 2 for t and 3 for y. So y prime equals 2 for t, 3 for y, so 2 squared plus 3 squared is 4 plus 9, which is 13. And then we multiply that by the step size of 0.2. All right, so now we have 3 plus 13 times 0.2. 3 plus 13 times 0.2 gives us 5.6. And so, again, this was just the first calculation. This first iteration of Euler's method gave us a y value of 5.6 for t equals 2.2. All right, so we just need to iterate this one more time. So starting from this y value, we want to approximate y at 2.4. Once we find this, we will be done. So we use the previous y value. We always start at the previous y value, so in this case 5.6. Again, we want to find y prime, but now with these two values plugged in. So instead of using the same y prime we just did, we want to recalculate y prime using t equals 2.2 and y equals 5.6. So 2.2 squared plus 5.6 squared gives us 36.2. And so again, to get this y prime value, here we plugged in the previous values, t and y, to calculate this next value, right? So the last thing we need next to y prime is the step size. The step size does not change. It's still 0.2. All right? So we have 5.6 plus 36.2 times the step size of 0.2. And as a result, we get 12.84, or about 12.8. So to summarize, Euler's method is something along these lines. So y1 you will calculate by using y0, the previous y value, plus y prime at t0, so the previous t and y value, and then that is being multiplied times the step size. So this is Euler's method. All right, let's keep going. All right, back to basics here. Starting with this table of x and f values, so basically x and y values, assuming that the step size, basically the width of each rectangle, is 20. They tell us to use a left sum to approximate area under the curve from 120 to 240. So that 120 to 240, that's the entire interval. And so with the width of 20, we know we're just going 1, 2, 3, 4, 5, 6. So we're summing up the area of 6 rectangles, and we're using a left sum. When using a left sum, if we know we have 6 rectangles, 1, 2, 3, 4, 5, 6, the height of each of the rectangles will come from the leftmost values, or the left sides of these rectangles. So what I mean is the left side of the first rectangle has a height of 4.8. The left side of the second rectangle is 4.93, and so on. And if we keep just using the left side for all 6 rectangles, that means we end up leaving off this rightmost value. So for a left sum, you add up basically, or you use all the heights of all the left values and then you leave off the rightmost y value, or rightmost height value. All right, so how do we apply this? We want to take the width, 20, and multiply it by the sum of all the heights. So we're summing up 4.8 plus 4.93 plus 5.07 plus 5.2 plus 5.33, 5.47. And really just adding all these up, multiplying these, will give us our answer. Let's go ahead and do this in Desmos real quick. So we want to do 20, and then in parentheses, 4.8 plus 4.93 plus 5.07 plus 5.2 plus 5.33 plus 5.47, and we get 616. So as a result, we get 616 for the left sum. So now, for the right sum, they say using a right sum, the area from 120 to 240 is 616. So really, it'd be very similar, except we would use all these y values and leave off the leftmost value. So we can just go in Desmos, hopefully, and change the very first value. We can leave the width. The width is the same. So we're starting at the 493 and going all the way to the very end. And next to the 5.47, we're just going to tack on 5.6. So see how we just barely changed what we typed in, because really the only difference is that the left sum uses the leftmost endpoint and the right sum uses the rightmost, and not the other way around. So 632 is the result of the right sum. And so we do see these values, but they've flip-flopped them from what should be right. And so both 1 and 2 are incorrect. So for the leftmost sum, use the leftmost values while leaving the right one off. For the right sum, use all the rightmost values and leave the most left value off. And then basically the formula is just the width and then sum of the heights. All right, let's keep rolling. Get into the fun stuff. Anti-derivatives, or anti-derivatives. So for something like this, starting with the basics, whenever you see t in a denominator, you ought to rewrite it, or I recommend rewriting it as t to the negative 20th. So whenever you have t in the denominator, rewrite it so that it's out of the denominator with the help of negative exponents. So again, this was not any derivative or antiderivative yet. This is just rewriting the original function. Now, when we take its antiderivative, we add 1 to the exponent, so t to the negative 19. And then we divide by whatever that new exponent is. So negative 19. And if we rewrote this, we'd get 1 over negative 19 t to the positive 19. So t to the negative 19, we can throw back to the denominator with a positive exponent. And then typically, I would recommend doing plus c, but in this case, it looks like they do not need it. And so just a negative 1/19 t to the 19th. All right. Now we're talking. All right. So with this one, we are given this crazy function to integrate, and the way we will do it, the method we will use will be u substitution. So in this case, our u value should be acted upon by some outer function, by some greater force. And in this case, you might ask, will it be the cosine or will it be the squared? And every time it'll be the cosine. It'll be the one that's really like a strict, distinct function that is acting upon this inside argument. So in this case, we identify our u. This will be a great u substitution problem to reference. So this is the u sub problem. Once we identify our u, we want to find the derivative, du. We can find the derivative by either using quotient rule, if you wish, or we could rewrite this original one as 11 times 11x plus 12 raised to the negative 1. We're allowed to rewrite that whole denominator up out of the denominator and then raise it to the negative 1 power. Now, why is this beneficial? When we take the derivative now, we can leave the 11, and now we just need to take the derivative of this using a little bit of chain rule. So we start by bringing the negative 1 out in front. We leave the inside stuff, and then we raise it to the negative 2. So we bring the negative 1 out, we subtract 1 to get negative 2. Keep in mind, currently we're just finding the derivative because we're performing the first parts of u substitution. Later on, once we have the integral all in terms of u and du, that's when we'll take the antiderivative. So that was just the first part of the du. We cannot forget to multiply by the derivative of the inside. The inside is 11x plus 12, so the derivative of the inside is 11. And so if we were to rewrite this real quick first, this, I'd probably take this negative 1, this 11, and this 11, and go ahead and multiply those together to get negative 121. And then I would take this that is raised to the negative 2, and I'd throw it in the denominator as 11x plus 12 to the positive 2. It helps to tack on dx, and then our next step usually is to solve for this dx, or get dx by itself on the right side, which means we have divided by this whole quotient, but dividing by this quotient is the same as multiplying by the reciprocal. So I'm going to multiply by 11x plus 12 squared over negative 121, and that's being multiplied by du. So this is what we will sub in to this little dx up there. So now that we have a u substitution and we have a dx substitution, it's time to substitute. So we're going to look at the original integral, keep the negative, keep the 66 cosine for the time being, and in place of the inside argument of cosine is where we put the u. And then we'll keep the denominator for the time being. We have 11x plus 12 squared, and then in place of the dx, again, is where we're plugging in this. So we're plugging in 11x plus 12 squared over negative 121, and that's times du. All right. So now keep in mind, with u sub, our goal is to eliminate all the x terms. Fortunately, as long as you've done everything correctly, the x terms should just cancel out nicely. What do we have left? We have the numbers to gather. So I would do negative 66 divided by negative 121. Both of them are divisible by 11. And of course, since there's two negatives, we can just eliminate the negatives and make everything positive. So 66 divided by 11 is 6. 121 divided by 11 is 11. So that was just 66 over 121 and reducing it to 6 over 11. What do we have left on the inside? Just cosine of u du. Now really, once you identify that 6 over 11, hopefully that's all you need to identify the answer. And then if we went a step further, the antiderivative of cosine is positive sine. So 6 over 11 positive sine of u, and then keep in mind u was actually 11 over 11 x plus 12. And then plus c. So a super, super crazy problem where the heavy lifting of the problem is identifying u and taking the derivative of u. So really that goes back to 1025 stuff. Unfortunately, it still is very beneficial to know derivative rules and chain rule or quotient rule, whichever you prefer, in these problems. And so once we identified the u and the dx, made the substitutions, all the simplifying was hopefully not that bad, and really it just left us with cosine of u. So this crazy integral just got simplified to cosine of u. So that's pretty crazy. And then again, just identifying really the coefficient, the 6 over 11 out in front, was the big deal. All right, let's keep it rolling. Pretty solid place to start. I think we've about covered this already, but let's do it real quick. We're taking the integral of negative sine from 2 to 4. So in geometric terms, we were finding the area under the curve of negative sine from 2 to 4, but the goal here really is just to find the antiderivative of negative sine, and then plug in 4, and then plug in 2, and then subtract the 2. So the first step, antiderivative of negative sine is cosine of x, because if you took the derivative of cosine of x, you'd get negative sine. So just positive cosine of x evaluated from 2 to 4. So we plug in the 4, we plug in the 2, and we subtract the 2. So this is very much a job for a calculator. Cosine of 4 minus cosine of 2, and we get negative 0.2. That is option B. So pretty solid little integral problem, but it covers the basics, and I could very much see a problem like this on the final, because it's testing your integral skills, so antiderivative, and then actually evaluating that integral. All right, another thing I could see on the final, solving this differential equation using a very similar method. We want to start with f prime, and the goal is to find what f is equal to, so the antiderivative. So starting with the antiderivative, I guess before we find the antiderivative, let's rewrite 3 over t. If it's 3 over t to the first power, we can bring that t up and raise it to the negative first power. So now we have everything rewritten in order to find the antiderivative. So f of t should be equal to 3. That 3 stays. And then t to the negative 1, we want to add 1 to the exponent. Oh, I'm mistaken. What happens when we add 1 to the exponent? We get t to the 0, but even worse, we would then divide by 0. I'm tripping. That's not how we want to do it. The one case where you don't want to rewrite your t terms that are in the denominator is this one. Whenever it's t to the first in the bottom, we want to remember that this is pretty much the same as 3 times 1 over t. So the 3 stays, but then what's the antiderivative of 1 over t? Natural log of t. So the derivative of natural log of x is 1 over x. Derivative of natural log of t is 1 over t, and you will always see absolute value bars around the t in the natural log. It's just a good habit to get into when you take the antiderivative. So, and then negative sine, I think we actually did this one in the last one. So negative sine of x has an antiderivative of positive cosine of x, or in this case cosine of t. And then we would add plus c. So we have 3 ln plus cosine plus c. And then really that tells us automatically that it's c. And then if we wanted to use the initial condition, I would recommend it. I recommend knowing how to do it. They're saying that when t equals 1, f equals 3, which means if we plug in 1, for all these t's. And then plug in 3 for f, we should be able to solve for c. So what do we know? We know ln of 1, we can type it into a calculator. Ln of 1 is 0, though, so that's convenient. 3 times 0 is just 0. So we have, if we subtract cosine of 1, we have 3 minus cosine of 1 equals c. So 2.45, if we rounded, probably about 2.5. And so when we tack on that 2.5 back to the original function, that's where that's coming from there. All right, hope that makes sense. I'm going to leave this here. I'm going to take a bathroom break. I'll be right back. All right. Hokie dokie. Second half of the session. Let's get into it. In this problem, they say if y satisfies the differential equation, then and y of 1 equals 1, then what does y of 1/2 equal? Okay, so the method here to use would be separation of variables. So what I recommend is getting y prime by itself first. All right, sorry, I'm out of breath. I'm like running up and down my stairs. All right. So the first step, I would say, is to, really it helps me to just rewrite y prime of t as just y prime. And then wherever we see y of t, I'm just going to use y. So keep in mind, this is not the same thing as like y prime times t or y times t. It's literally just like y prime and y. That's a very important distinction. So writing this is the same as this. And then, so the first thing I'm going to do is subtract this whole term to the right side. So we're going to have a negative t squared over t squared plus 1 times y. So we've moved that entire term to the right side. Now what we can do is divide by t to get y prime by itself. When we divide by t, that's like the same thing as multiplying by 1 over t, which as a result would cancel one of these t's with this t. So we can get rid of this, and we can get rid of this, and we have this really, I should have written this over here. So t squared plus 1 and then times y. All right. So now we have y prime by itself. Y prime is equivalent to dy over dt, which I would also recommend rewriting the y prime as in this case, because we want to use the method known as separation of variables. In separation of variables, basically we want to get the t terms, all the t terms, and the dt on the right side while getting all the y terms on the left side. So if we divide by y, we will have 1 over y dy, and if we multiply this dt over to the right side, altogether we should have on the right side negative t over t squared plus 1 dt. So now we have y terms and dy on the left side and t terms and dt on the right side. And now the next step is to integrate both sides or find the antiderivative of both sides. 1 over y, we see this example a lot, we end up getting natural log of y. And it might be important to put absolute value bars around the y just in case, you never know. And now this one. This might use some previous, skills regarding integrals. So when we see something like this and there's no direct integral answer for it, no direct antiderivative, I recommend using u substitution. In this case, u will equal that denominator, the term with the higher degree, so that when we take the derivative of u, we get 2t. So we could say 2t dt. We can solve for dt by dividing by 2t. This gives us something to sub in place of the dt, and then we'll sub in the t squared plus 1 in place, or we'll sub in u in place of t squared plus 1. So before we find the integral, we're just gonna, we'll keep it here, that's fine. So we are replacing the t squared plus 1 on the bottom with u, and the dt over here with du over 2t. So now our goal is to cancel all the t terms that we see, which we can do here and here. What are we left with? We're left with a negative over a 2. So basically a negative 1 over 2. Negative 1 over 2. There's still a 1 on top technically. du's over here, and we leave that u on the bottom. Hopefully that makes sense. We've gotten all the t terms here in terms of u. So that allows us to evaluate this integral now. So take the antiderivative of this, and we get negative 1/2 natural log of absolute value of u plus c. And now getting everything back in terms of t, we cannot forget to plug the u back in. That is t squared plus 1 plus c. So getting back to the main part of the problem here, we're going to bring this down here. We're going to bring this result from the right side over here. We're going to look at what we have. So far, we have gotten y prime by itself. We called y prime dy over dt. That allows us to separate the variables, y terms, t terms. Then we could integrate both sides. We got ln of absolute value of y. And then we got all this from doing u sub on the right side. So negative 1/2 of ln, negative 1/2 times ln of t squared plus 1 plus c. Okay, now the next step is to plug in the initial condition in order to solve for c. But actually I might suggest let's solve for y first. So let's get y by itself. Remember, anytime you need to eliminate natural log, we want to make e the base of both sides. As a result, we get, I'm going to move this down, excuse this. As a result, we cancel the e and the ln, leaving us with y equals e to the negative 1/2 ln of t squared plus 1 And then the plus C up here, I don't know if y'all remember from the really from this section, a common thing you can do with this plus C up here is really just bringing it out in front as a constant. So I would often recommend that, kind of just skipping that step. You can jump right to this. All right, so our goal now is to solve for C, and again, we will do that by using the initial condition, or this condition they give us. So they're telling us that when t equals 1, then y should equal 1, which means if we plug in 1 for y and 1 for t, it should allow us to solve for C. So what do we have up here? We have 1 equals ce to the negative 1/2 ln of 1 squared plus 1, which is ln of 2. All right, so let's calculate this, and then we'll just divide it to the other side to get c by itself. So e to the negative 1/2 times the natural log of 2. And we get 0.707. And now if we subtract that to the other side, so 1 minus this point, what was it, 0.707, we will get I'll use a few more decimals to be a little more exact here. We get 0.293. And again, that was solving for, oh, I'm so stupid, I'm so sorry. We were supposed to divide by that value, so 1 divided by that, because dividing by this e term, dividing this over here would have gotten us c by itself. Whoever's watching this, thank you for bearing with me today. I'm really only human, and it's hard to do some of these problems in one successive thing. Sorry, Mom. Declining my mom on Mother's Day. That's what I'm doing for these. That's pretty bad, huh? Sorry, Mom. 1.14. Sorry, 1.414 is our result, is our C value. All right. So our C value is 1.14. That only tells us what this value up here is, 1.14. I think I keep saying it wrong. All right. Y is equal to 1.414. So now, what are they asking? They want to know what y of 1/2 is. So we are plugging in 1/2 into t in here. Because now that we have C, that allows us to have a complete and exact solution function. So we are plugging in 1/2 for t. Let's open up Desmos. 1.414 e to the negative 1/2 negative, I'll just do negative 0.5 times the natural log keep skipping over it. There we go. Natural log of t squared, and in place of t we're plugging in 1/2. So t squared plus 1. So 1/2 squared plus 1. As a result, we get 1.26. If we round 1.26 up, we get 1.3. So serious problem here. We solved for y prime. We separated the variables. We integrated both sides. We used u substitution along the way for part of the integration. We got y by itself by eliminating the ln, by making e the base. We solved for c by using the initial condition they gave us. And then, or I guess it's just a condition. I don't think initial condition. Anyway, we plugged those values in, solved for c. Then we plugged in the 1/2 for t. All right, very much a problem I could see on the final exam. Let's keep it going. I want to just work through as many as I can. Thanks for bearing with me again. Let's jump into it. The growth rate of a particular bacteria is modeled by this differential equation, and they tell us some information. All right, the nice thing about this differential equation, k times p, is that anytime you see this, we will already know that the solution to this differential equation will be p equals c e to the k times t. It's very much the a equals pe to the rt you might be familiar with. It's the same exact thing. And again, whenever we know that the differential equation is just k times p, that's how we know we can just jump straight to this. So we are using this. They tell us that the population quadruples every 14 hours. So it quadruples every 14 hours. They say initially there are 300 bacteria cells. The initial value is always the C value, this constant out in front. And so what we want to do first, I believe, is solve for K. So all we know is that every 14 hours, it quadruples in size, which means if it's starting from 300, to quadruple that takes us to 1200. So it's almost like they're giving us an ordered pair, a T and a P value, an X and a Y value, for example. Or for, whatever. All right, so 14 and 1200. So starting at 300, the population should grow to 1200. And our goal here first is to solve for K. Once we have K, we'll plug things back into this. Namely, we'll plug in 200,000 in for P. We know our C. We'll have found our K, and then our goal will be to solve for T. Once we have T, we'll try to use that to figure out the whole time and day situation or dilemma. So starting by solving for K in this equation, we always start by dividing by the initial amount. That gives us that 4. 1200 divided by 300 equals 4. And so 4 is equal to e to the 14k, or k times 14. We eliminate e by taking the natural log of both sides. We have ln of 4 is now equal to 14k. We get k by itself by dividing by 14. Let's take a moment to calculate this in Desmos. ln of 4 divided by 14. And we get 0.099. All right. So we get 0.099 for K. So now, again, we want to go back to this original equation. And now they're asking, when is the earliest? So we're solving for T. When is the earliest the necessary 200,000 bacteria cells will be ready? So we know that C is still 300. We have E to the K, which is 0.099 that we just found out, times T. So this is the second part of the problem. We are solving for T in a very similar method that we just used to solve for K. So again, we start by dividing by 300. So we can get rid of some zeros, and then the best we have is 2,000 divided by 3. I don't know what that is off the top of my head, maybe like 6 something, 666. 2,000 divided by 3. We get 666 point, I'll just say 67. And we just divided that 300, so we're left with this e to the 0.099t. We can take the natural log to eliminate the e, and then it'll leave us really with just this 0.099t. So we divide by that 0.099t to get, or just by the 0.099 to get t by itself. So we're going to calculate this to get the value of t. So I'm going to do ln of all this. Nice. And then we're dividing that by 0.099. That gives us 65.67. So I will always round this value up in this problem, because we always want to round up, because if we round down, then really we will not have reached the full time it takes to hit the population desired, that 200,000. So we want to round up no matter what the decimal is in this problem. So 66 hours is how long we need. How do we use that? We know that the experiment is starting at 9 p.m. on October 2nd. 9 p.m. on October 2nd. We want to add 66 hours to that, okay? So if we add, well, let's think about this. How many days is 66 hours? If we divide 66 by 24, we're getting 2.75 days. We are adding 2 days and then 0.75 days. But we don't want to use 0.75 days. We want to figure out how many hours is 0.75 days. So what we do is 0.75 times 24. And it tells us 18 hours is the equivalent of 0.75 days. So really, 2.75 days is equivalent to 2 days and 18 hours. So this is what we're adding to October 2nd. I hate that this is here. Let's move this. All right. All right. Let's break it down. Let's start with adding the 2 days to October 2nd. Adding 2 days takes us to October 4th at 9 p.m. Now, if we add 3 hours of these 18 hours, that'll leave us with only 15 hours to add, but it'll take us, more importantly, to midnight or 12 a.m. But not on October 4th. We've gone to the next day, since we added 3 hours and got to midnight on the next day, right? So we have 12 a.m. or midnight on October 5th plus 15 hours. That's what we're trying to figure out. So if we add another 12 hours, that'll take us to 12 p.m. That's taking us to noon on October 5th. And if we've just added 12 of these 15 hours, all we have left is to add 3 hours. So that takes us to 3 p.m. on October 5th. I hope that breaking it up in terms of breaking up method, like adding 3 hours, adding 12 hours, adding a certain amount of days, all that makes sense. That's just how my brain thinks about it. I think it's helpful. I hope it's helpful. If you have any questions, let me know. I don't know. Let's just keep rolling. So 3 p.m. October 5th is the answer. Let's keep rolling. So what do we have? We have a few more, and then we're doing probability. All right, perfect. So this is a great problem. Again, this is the fixed law problem. Okay, let's jump into it. Fixed law, again, is the, I can never remember what the dy over dt part is. I think it's like dc over dt. I don't know. I'm just going to use dy over dt. It shouldn't matter. It's k times the area divided by the thickness times the change in concentration. Now with this one, the change in concentration is very particular, I guess. So what it should be is n, the value of the, actually I think it's the outside concentration. So I'll just do CO for C outside minus CI for C inside. This is delta C. This is the difference or the change in concentration. The change means from outside to inside. And they tell us that the concentration of the outside of the cell is 1.3. And that does not change, which means delta C is 1.3. Or the start of delta C is 1.3 minus the minus the inside concentration, CI. And CI, I remember now, CI can actually be represented with N, where N represents the concentration. So they say the initial concentration inside the cell is represented by N, and then later it's this N. So because the inside concentration of the cell is changing, that's why we can't use just one of the two values they give us, right? So they tell us the outside concentration stays the same, but they tell us the inside concentration is changing. So that's why we have to use N in its place, because it's changing. And I remembered, because it's N, it's actually dN over dt. All right. So now we are going to plug this in here along with the area and the thickness obtained from the problem. Let's give it a shot. So try to do this without having to zoom in and out. I know everyone loves that. All right, dn over dt equals k. K is what we do not know. K is what we're looking for. Eventually, the area is the 5 times 10 to the negative 8. 5 times 10 to the negative 8. We are dividing this by the thickness. That is 8 times 10 to the negative 8. The 10 to the negative 8s automatically will be able to cancel every time. So we are left with just 5 over 8. Very nice. Then delta C is the 1.3 minus n. We have a much easier differential equation to solve here. We're going to solve this with separation of variables. So we have dn is like our dy. And so we want to get this 1.3 minus n to the right side to be with its n, pair or whatever. And then we want to move the dt to the right side to be with the k times 5/8. I'm going to call those our t terms. So we're going to start by dividing by 1.3 minus n, leave the dn, and simultaneously go ahead and multiply the dt to the right side. So we have this times dn, this times dt. We take the integral now of both sides that we have it separated, now that we have it separated. And so we want to find the integral of both these sides, the antiderivatives. I'm going to try to move this stuff here. And let's keep working this out. So we essentially could use u substitution here. For the first one, I'll just kind of show you a shortcut. Because we have n to the first power on the bottom, then what we want to use, we want to treat it as if it were 1 over n, and we're taking the antiderivative. So what we get as a result is the natural log of 1.3 minus n in the absolute value bars. The catch is that the derivative of this inside, the 1.3 minus n, is negative 1. And so we want to make sure we tack on a negative to the outside or multiply it by negative 1. Because if we took the derivative of this, we would get this, but it would be negative. So we need to tack on this negative so that it negates this negative, so that the negative is not in the result up here. So basically just negative ln of this. All right. If you want more explanation, go watch the videos I've done on this. Hopefully it makes more sense. All right, let's keep going. So we're finding the antiderivative of 5/8 k with respect to t. So really 5/8 k is just a constant. And so all we do is tack on a t. We're treating it as if it were just like the integral of 4. That would be 4t. So 5/8 k is 5/8 k times t. And we'll go ahead and add our constant plus c. Now, the question is, what do they tell us? They tell us that the initial concentration inside the cell is when n equals 0. For n of 0, we get 1.1, which means when t equals 0, n equals 1.1. Now, before we plug that in, I might go ahead and solve for n as best we can. So we want to solve for this little n in here. The way we can do that is by first negating both sides. So negating both sides, we get positive ln of 1.3 minus n. We get negative 5/8 k kt, and then plus a constant, but you're negating that. Regardless, it's just a constant, so it kind of just absorbs that negative. Okay. So now we want to eliminate the natural log. So we take the e and make it the base of both sides. That leaves us with 1.3 minus n equals ce to the negative 5/8 kt. And so again, this plus c we've just thrown in the front as the constant, I suppose, as the coefficient. So now, to get n by itself, what I'll do is I'll kind of do maybe a different method you might not use, I don't know. So I'm going to add this n over here, and I'm going to subtract all this stuff over here. So kind of flip-flopping these to get the positive n over here, and I'll subtract CE to the negative 5/8 KT here. Now we have a function for n for which we can solve for C. All right, crushing it so far. Let's see what we can do. When we plug in t equals 0, they tell us that n should equal 1.1. So if we plug in t equals 0, when we plug in t equals 0 to this, really the whole exponent is going to go to 0 because we're multiplying the whole exponent by 0. So we get 1.3 minus c e to the 0 equals our n value of 1.1. And keep in mind, e to the 0 is just 1 because anything raised to the 0 power is 1. So we just have c times 1, which is c. So we have 1.3 minus c is 1.1. You could think about it as like if we did 1.3 minus something, what would give us 1.1? Or you could just perform the actual subtraction here. So flip-flopping these, subtracting the 1.1 to the left, adding the c to the right, we get c is 0.2. So we can plug that in back up here in place of the c. In place of the c, we have 0.2. And our last step, sort of, is using this last condition, n of 1 equals 1.29. So we are plugging in t equals 1 and n equals 1.29. This is what we should need to solve for k here. So we will do just that. We're doing 1.3 minus 0.2 e to the negative 5/8 times k, which we don't know, times t, which is 1. So really just, we can leave it off. And then equals n, which is 1.29. So now solving this for k. All right, let's subtract the 1.3. So we'll have negative 0.2 e to the negative 5/8 k equals negative 0.01. 1.29 minus 1.3 is negative 0.01. We can divide by negative 0.2 to get e by itself. Dividing by that, let's do it in Desmos real quick. They're both negative, so it'll become positive, but that should give us 0.05. And then, to get closer to getting k by itself, we want to take the natural log of both sides to eliminate the e. That'll give us negative 5/8 k equal to ln of .05. That's a negative 2.996. And then to get k by itself, we multiply both sides by the reciprocal of negative 5/8. As a result, we get, negative 8 over 5. So times negative 8 over 5, and we get 4.79. And this k value will round up to k equals 5. All right. Super fun fixed law problem. Hope that makes some sense. Let's keep it going. Now into the classic probability stuff. After doing probability this past couple weeks, you probably forgot all this other mess was in this section. I know I did. I was so used to probability stuff. All right, let's keep it going. So they tell us we have a 52 card deck, a standard deck, and you draw a royal card. So you draw a jack, queen, or king from 52 cards. And then without replacing the first card, So you have not put back the 1 card. So you are drawing a second card from the remaining 51 cards. What's the probability that the second card is a jack, queen, or a king? Now keep in mind, you've already taken one of the jack, queen, or kings from the deck, from which or of which originally there were 12 total either jack, queen, or kings, or 12 royal cards. So there's a jack, queen, or king per suit, and there are 4 suits, so 3 times 4 gives us 12 originally, but you've taken one away from that 12. So really, once you've already taken one, all that's left to choose from is 11 royal cards from the total remaining 51 cards, and that's all they're looking for. Probably over-explained the crud out of that, so hopefully it makes sense. If not, feel free to watch the videos or let me know if you have any questions. Hope no one sent me any emails. Just want to make sure. Not that I see. Alright. Jumping into this problem. I could very well see this on the final. It just seems like a good problem to ask, in my opinion. A certain blood test accurately indicates the presence of the disease 95% of the time when it's actually present. The test indicates the presence of the disease 0.4% of the time when it's not present. If 1% of the population has the disease, what percent will test negative? And so I like to just break this down with the tree situation. So we're going to do if 1% has the disease, we know that 0.01 of the population has the disease, which means that naturally 99% of the population does not have the disease. So I'm going to say disease, no disease, D and ND. And so of these 1%, of this 0.01 with the disease, it says the test will indicate the presence of the disease 95% of the time when it's actually there. So that means 0.95 should give you a true indication of the presence of the disease, which means of the 1% of the 0.01 that has the disease, that means 5% of them, 4 or 5%, for 5% of them, it will not indicate the presence of that disease. And so for the 99% of the people who do not have the disease, it says it's going to indicate the presence of the disease even when it's not present 0.4% of the time. Now 0.4% as a decimal is 0.004, which means for those who do not have the disease, 99.6% of the time, that's not right, 99.6% of the time, or 0.996, it will not indicate the presence of the disease because they don't have it, right? So all we need to do is figure out what percentage of the total population will test negative. Keep in mind the way we've organized this is that these are all the negative tests. So we can really just calculate these paths here, these stems, these whatever you want to call them. So we're just going to do 0.01, this value at the top, times 0.05. This will give us the the false negative. So of the people that have the disease, this is going to be the amount or the percentage that it says they do not have the disease. And then we want to add that to the 0.99 times 0.996. And so this is the false negatives plus the true negatives. So let's go ahead and calculate that in Desmos real quick and get our answer. We'll keep it rolling. 0.01 times 0.05 plus 0.99 times 0.996. That'll give us 0.98654. So 0.98654 as a decimal, then of course as a percentage, 98.6-ish%. All right, hope this tree diagram situation is helpful. Let's keep it rolling. I'm very proud of this problem. This problem used to give me nightmares, and we finally figured it out this semester. So I wanted to share this one with you in case they talk about phenotypes and genotypes, the most unrelated thing to calculus ever. Let's jump into it. So in this one, they give us all these, genotypes and phenotypes. They say if a parent with genotype, lowercase aa, capital QQ, and parent with genotype, AAQQ, have a child, what's the probability their child has phenotype with a trait 1? So let's talk genotypes first. So with each parent, you want to figure out what are all the combinations of A's and Q's per parent. So for parent 1, we have AAQQ. So the only possible options for A and Q together are a lowercase a with an uppercase Q, because that's all they have. They have lowercase a's and uppercase q's. So that's all we get for the first parent, right? So we can just throw the first parent here. It shouldn't matter. And then for the second parent, we have a capital A, lowercase a, capital Q, lowercase q. Now here's where all the options come from. Again, we're finding all the combinations of A's and Q's that could come from this parent. So we could have capital A, capital Q. We could have capital A, lowercase q. We could have lowercase a, capital Q. We could have lowercase a, lowercase q. And so we're going to lay these options out on the across the top here. So we're going to do capital A, capital Q. We're going to do capital A, lowercase q. We're going to do lowercase uppercase and lowercase. And what we're doing is finding the intersections of each of these. So I believe it just goes like this. You sort of just combine them at this point. So capital A, Q, Q. So you combine the A's and combine the Q's, usually putting capitals first. And then A, Q, Q, and then lowercase, and then uppercase, lowercase. All right. A little crammed at the end there, but hopefully this makes sense. So we just kind of intersected the lowercase a, capital Q with all these other combinations here. All right. So now let's identify the number of these that have trait 1. So all of these are the possible genotypes of the child between these two parents. So let's identify which of these children, these child options, has trait 1. Okay, so AAQQ, so that's trait 2, that's out of there. Uppercase, lowercase, uppercase, lowercase, that's also trait 2. Lowercase, lower, that's an A, by the way, right here. AA, capital QQ, that is a trait 1. So we have 1 out of 4 so far. And then the last one, lowercase a's, 1 uppercase q, is also trait 1. So that means not the first one, not the second one, but the last 2 out of 4 could possibly be trait 1. So that's 1/2 of all the possible child phenotype options. I hope that makes sense. That's where this 1/2 is coming from. Just wanted to do one example of that to give some insight on the genotype phenotype situation. All right. Don't think I have too many more problems laid out, but a lot of them are very Excel oriented. Let's see if we can turn the iPad. That's nice, right? Okay, so we're going to do this in Excel. So I'm going to bring this over here. We're going to open up Excel, and I'm going to do some typing. Just a sec. All right. All right, so in this problem, they ask in the data set below what percentage of the variation in y is due to a linear relationship with x. Whenever you see this, this goes back to when you learned something about correlation coefficients or R values. So the correlation coefficient represents like a, the correlation between x and y, how strong or weak it is, whether it's in a positive direction or a negative direction, like a positive slope or negative slope. Now, whenever they ask what's the percentage of variation in y due to a linear relationship in x, that phrase, whenever you see that phrase, I want you to think about r squared. It's not just r, but the correlation coefficient squared. That's what they're looking for. So if we just plug these values in, I'm going to just do it how they have it plugged in, 13.8 and so on, 20.3. Just making sure all these match up here. Let's try to zoom in on this real quick now that we know what we're looking for. So 10.2, 13.8, 20.3, 23. All right. Now that we have these, there's a couple of different ways you can go about it. I think one way I prefer is highlighting these, inserting a scatter, and then you can see, if we did like a trend line with these dots would be pretty off that trend line. But doing the whole trend line thing is actually where we can find an answer here. If we click on the chart, go to add chart element, go to trend line, more options. Down here, there's a button, there's a box that says display r squared value on the chart. R squared is the percentage of variation due to a linear relationship of y and x and yada yada. 0.7231 or 72%. Or 72.31%. All right, so that's it. That's all it is. And then there are other problems, I suppose, that do use just calculating the r value. So I might just say, if you wanted to, you could do the function equals correl, and it says returns the correlation coefficient between two data sets. So if you double click on that, the array 1, I think they just want the x values. And then you put a comma and you highlight the y values. Again, this output is the correlation coefficient, which is the r value, which means if we take this and we square it, I wonder if we can do this all in one thing here, raise it to the second power, look at that, we get 0.72308, which rounds to 72.31%. All right, let's keep it going. In this problem, they ask us to use the empirical rule to find basically the probability or the proportion of the data that's between z values 0 and 3. Now, if you think back to an empirical rule curve or a normal curve, that's where we had that bell curve, where in the middle we have let's see if I can draw it real quick down here. It's a little off because I'm a little far away here, but it's the normal curve where in the middle we have the mean, and then to get to each end of this curve we add 1, 2, 3 standard deviations, and then to get to the other end we subtract 1, 2, and 3 standard deviations. And so what they're asking is, what's the percentage of the area under this curve that is between the 0 standard deviation, which is another way of saying 0 standard deviations away from the mean would be at the mean. So what's the percentage between 0 and positive 3 standard deviations? So visually, we could tell this is about 50% of the entire curve. Now, to use Excel is what I would recommend, but that's just a way you can visually kind of make sense of this almost 50%. Okay, so we want to use a function called norm dist or norm sdist. Yeah, we're going to use norm sdist. Norm sdist allows you to just plug in the z value, and then wherever it says cumulative, you're going to type 1. So we want the z value, we want to plug in the z value 3. we want to plug in the z value of 0 and then subtract the two results that we get. So 3 comma 1, and then we'll go ahead and do this all in one. We'll do minus norm s dist of the z-score of 0 comma 1. And as a result, it's going ahead and finding the difference, or the the percentage of the area under the curve between z equals 0 and z equals 3. And so that's 49.85%. All right, let's see what else we have. I think this might be the last one I have. So I may just call it here unless anyone has any questions. Let's see. After I do this one, of course. Got through a lot more problems than I imagined, even with making a fool of myself at the start. But hopefully, really, I just want you all to be able to learn from my mistakes at the start there, and learn that Excel is very finicky in how you plug things in. Oh, I'm stupid. I just have to turn my iPad. I'm spending too much time on the wrong thing. Alright. So I just want you all to learn from the very start that the Excel plugging in is very finicky, and so I hope that was a good lesson at the start. It's also just me just embarrassing myself, so that's fun. Let's keep it going. Alright. But below are two frequency distributions. The populations are the same, which of the following statements are true. So with this problem, remember the thing to keep in mind basically was the mean in general. You can always kind of assume the mean is about in the middle-ish of the distribution. So between about 3 and 10, it should be at about 6 or 7 over here. So this is where the mean should be over here. And then naturally, if this is like here to here, then the mean's probably where that max, that high bar is, right? So about here. So the mean here is at about 7, and then the mean here is at about 5. And then for standard deviation is describing the spread of the data. How spread out is it? The more spread out it is, the higher the standard deviation is. So this data set is more spread out. So this has a larger or a greater standard deviation. Whereas this one is very narrow. It's very tightly packed data. It's not as spread out, which means it's I'll just say small standard deviation. So both the mean and standard deviation of the first population are greater than the second. That is true because the mean is about 7, and visually the standard deviation is much larger than this narrowly spread out data. All right. So since we have a few minutes, some things I will summarize, starting from the top. Go way back, go way back, go way back. All right. And we covered a lot. That was pretty good. All right. I would 100% know how to find an antiderivative of a function. I would go over your antiderivative rules. That's reverse power rule. I would focus on knowing that 1 over t goes to ln of t. The trig functions you'll see, sine and cosine, just know those antiderivatives. I would understand u substitution, practice a few u sub problems. I would understand how to use Excel to go about these ridiculous problems. So a lot of it's just like plugging in the x values, plugging in the y values, and then just understanding the formulas for left rectangular sums, right rectangular sums, midpoint rectangular sums, trapezoidal sums. I think that's it. Direct versus inversely proportional things. Fixed law could be worth it. Odds might be slim, but I could see them throwing one of them on there. Definitely something regarding predator-prey. That's got to be on there. So maybe practice a few of those. SIR model, same kind of like that. Maybe that's the predator-prey model they would do. SIR is a little more popular, I think. So I could totally see them doing that. Understand slope fields. like basically how to find the slope when given certain t and y values, make sense of equilibrium solutions where y prime equals 0. Sorry, it's taking a second to load. Just need to leave it. There we go. So slope fields, equilibrium solutions, unstable versus stable. Pretty much everything we've covered today. Euler's method. I feel like everything we've covered has been a great representation of like the general fundamental things you ought to know from 1026. So there's the left and right sums, which we mentioned. Again, antiderivative, u substitution, integral, evaluating integrals from an actual like bound a to b, solving these differential equations, so antiderivatives, and solving for c values, solving for those initial conditions, solving for c using initial conditions, using separation of variables. Could be very large. It could play into one or two problems. That's what I mean by large. This, I can see a problem like this on the final as one of like the more difficult problems. Again, that's like just separation of variables in a sense. There's that fixed law problem, which, you know, I don't know. It might be on there, might not be on there, but it's one of the hardest problems if you do get it. So it might be on there. I don't know. Definitely, you know, basic probability stuff, all the stuff from the last quiz, I would understand the fundamentals of. This is a good little problem. I don't know. At this point, you know, I feel like all the fundamentals we've seen. This stuff is just, who knows what's going to be on there. But stuff you can plug in to Excel like this could play a role. I could see 100% they're going to have something regarding z-scores or standard deviations away from the curve. So a z-score is the number of standard deviations something is away from the mean. And then these are just like, you know, regular distributions, analyzing mean and standard deviation. We covered a lot today. Whoever watched the start, again, thanks for bearing with me. That's me just not being warmed up and prepared. But again, I hope you learned from it. I hope everyone has a great rest of finals. You know, stay taking care of yourself. Don't take anything too seriously. You know, just study, do the best you can. Make sure you're getting plenty of sleep, eating properly, drinking water. Yeah, that's about it. That's all I got. Hope everyone's doing all right. I started off a little rough myself today. I'm glad we got through this together. If you found this YouTube or my videos helpful at all this semester, please consider donating anything you got to Carter D, that's 3 E's, and if it asks for the last 4 digits of my phone number, it is 6910. Thank you all so much. I'm so grateful I can share these videos and do this for you all. It's a really good feeling to be able to help so many people. Yeah, all right. I might just wrap it up there. Thank you all for watching. Thanks for sticking with me. Again, hope finals go smoothly. All right.